26. So far we have seen the following, which is we know how to build a preamplifier with offset cancellation, and we know how to build a latch, and from what we discussed, it didn't seem quite as straightforward to cancel the offset of a latch as it was to cancel the offset of a preamplifier. The very common trick used is to put the preamplifier before the latch, because you know that putting an amplifier up front reduces the equivalent input referred offset of the latch, and now you end up with the preamplifier offset, and it is quite straightforward to cancel the preamplifier offset itself, as we have seen using circuit example. Now the next thing is to figure out how to put the preamplifier and the latch together so that the combination of the preamplifier and the latch operates properly. It's actually quite straightforward. Let's get to it right away. These capacitors labeled C are the coupling capacitors onto which the references as well as the offset of the preamp are stored in a differential fashion. If I call this V ref P, this is V in P, VIM and V ref M. During the special phase called phi AZ, the references are shorted, whereas during phi AZ bar, the inputs are shorted to the left plates of the capacitor. Alright, and during the auto zero phase, the amplifier is put in closed loop so that the output voltage developed is exactly, it's almost equal to the input referred offset of the preamp. And this is all stuff that you know. And the capacitors differentially hold Vref P minus Vref M minus the offset. So during amplification, the effective voltage between the positive and negative terminals of the amplifier, that is these guys here, is nothing but VIP minus VIM minus Vref P minus Vref M, okay, minus V offset. The positive offset of the preamp is compensated for, so you get offset free operation. And we saw that finite gain of the preamplifier has the effect of modifying the stored offset from what should ideally have been V offset to V offset times A by A plus 1. So it is important from both the offset cancellation perspective as well as amplification later on to have a high gain for the preamplifier. So this is one guy. The other guy we have here is the latch. I'm not going to get into the details of the latch, you already know most of this stuff, so I'm going to just draw a black box with the clocks. Okay, so this is VDD, this is ground, we have phi 1, phi 2 and RST. These nodes basically correspond to the nodes X and Y of the regenerative input pair of the four transistors inside that box. That's the latch cross coupled inverters. The wire going to supply is disabled when those two parasitic nodes at those points are being charged to the appropriate value, and the latch is regenerated. You need to remove prior memory. The reset switch basically goes and zaps those two nodes together so that the two become approximately equal to VDD by 2. To make life more easy or things easier to remember, we can name these things by more appropriate names. The LC phase, which stands for, what do you think it could stand for? LC stands for latch connect. You know, when you turn on these two switches here, the latch action, which is regeneration, is enabled. So I like to call these LE. So you enable the latch during the phase LE. I'll call this LRST, which is just short for latch reset. Now let's try and so clearly you have to connect the preamp output to the latch input. So let me do that. And you want the preamp output to be connected to the latch input only when can LC be on at the same time as phi AZ? No, because during phi AZ the output of the preamplifier is V offset. It's got nothing to do with the input. Clearly, if you want to draw a timing diagram, so in flash ADCs, once you know what the preamp and the latch, which are pretty straightforward circuits, the rest of it is only timing. You got to be absolutely sure that you don't screw up operation of the comparator by bad timing. Let me conceptually draw a diagram, a timing diagram. Let's say this was phi AZ. So this is the amount of time during which the preamp is put into the auto zero mode. So once the preamp is, has come out of auto zero, what can happen next? I mean, so once phi AZ is low, automatically phi AZ bar becomes high. So the input is connected to the connected to the preamp through these two capacitors which do the reference subtraction. That basically means that the output of the preamp in principle is, so around this time the output of the preamp must reach, if assume that the preamp is an instantaneously fast and has a gain A, what do you think will happen to the output of the preamp around the time of the red arrow? What will be the differential output of the preamp? See, phi AZ has gone down, so which means the amplifier is in what mode? Is it in is there a feedback loop around the op amp, or is it amplifying? It is amplifying. So, and what is it amplifying? It is amplifying the input between its plus and minus terminals. So the differential output is going to be A times VIP minus VIM minus Vref P minus Vref M. The differential input between the plus and minus terminals of the preamp is nothing but VIP minus VIM minus Vref P minus Vref M, and the offset terms, of course. So the output of the preamp will simply be the gain of the preamp multiplied by the differential input. In principle, if the preamp was infinitely fast, it should be ready right away, around there. In practice, the preamp will take some time. Things don't just happen very quickly. So it takes time to charge up parasitic capacitances and so on. So it takes a little while. When do you think is an appropriate time to connect the turn LC on? I mean, see, you can do two things. One is you can wait for the output of the preamp to settle and then connect it to the latch. What do you think happens as soon as you connect it to the latch then? It will again drop because those two capacitors, the parasitic capacitors at the input of the latch, have not yet been charged. And what the preamp has done is basically it's attempting to push the difference between these two nodes here to A times the difference. So suddenly if you connect two capacitors which have been uncharged, momentarily the output will dip and again attempt to go back. Rather than do that, you might as well have connected it to the preamp right away. Okay, there's no earthly reason to wait. A reasonable thing to do would be therefore to wait for you want to make sure that the auto zero phase is over before you connect it to the latch. So this is LC. So once, and hopefully, so this is the amount of time the preamp has got for amplification. So the longer this LC time is, in principle, the lower the bandwidth of the preamp can be, and the output will still remain A times the difference between the input and the reference at the end of the LC period. Now once LC goes low, what do you want to do next? At the end of LC, the two parasitic capacitances at the input of the latch have been charged to A times VIP minus VIM minus Vref P minus Vref M. So the next job is to simply enable the latch so that regeneration can happen, and that is also quite straightforward. You wait for a small time, you enable the latch. So once the latch has been enabled, when is the decision available? I mean, in principle, the decision, is available probably around here. And the longer LE is, what can you say about the sensitivity of the latch? In principle, to resolve 0 to a logic level, it takes an infinite amount of time. But in practice, you put a limit to how good your resolution needs to be. And you say, okay, so I have only so much time for LE, so this is the best I can do. So the longer LE is, the smaller is the difference you can resolve. I mean, it's pretty much like this. So if it's even in an interview, right? If you have a candidate who's clearly good or clearly bad, you either take him in or chuck him out right away. The people who take long to interview are the border cases. You understand? You don't want to spend all your time and energy interviewing somebody who clearly seems great, or you don't want to interview somebody who doesn't know 1 plus 2 is 4, right? So these the guys at the border are always more difficult to resolve. The same thing here too. So things become difficult only when there are borderline cases. So before LE goes down, what should I do? If I reset the latch, what happens? I should hold on to the decision, no? Before I do anything to the 2 voltages which have regenerated, I should figure out what I have done. That is, hold on to the decision made, and then I can go and reset the latch. So I need another clock, which basically, for example, a simple way of holding information is to hold what happens. Okay, so this is reached. So these 2 nodes have reached valid logic levels a little before the end of LE. So one way to hold on to the logical decision that they have made is to sample this output, these outputs, a little before LE falls, and then for a momentary, you just turn on this LD for a short while, and then you open the switch so that this voltage has been held where? It's been held on the output parasitic, on the input parasitic capacitances of the 2 inverters, right? And again, using my artistic license, I will just call them LD, latch delayed. What else? What else should I do? So after I've held on to the decision, what is my latch is useless now? I can reset, but should I wait for LE to fall off? Let's argue about this. Clearly, after LE falls off, resetting is harmless, right? That we know works. What about trying to reset it even when LE is high? So if LE is high and you try and reset the 2 nodes, what will happen? The 2 voltages will tend to come together, and it's like having 2 inverters connected with the outputs at mid-rail. If you have a live CMOS inverter with the output being mid-rail, that basically means that both the transistors are in saturation and they'll draw a huge current from the supply. So while in principle there is nothing wrong with trying to reset even when LE is high, in the interest of power dissipation, it makes sense for LE to fall off before you turn the latch reset LRST on. So the one question asked is, why do you want LD to fall off before LE? Once LE is down, weird things start happening to those nodes, right? So you want to grab the output before those decisions get screwed up by any other operation. So as you see, the diagram, at first sight, the clock generator looks intimidating, but you know that there is method in the madness, right? It's all fairly straightforward and there's no rocket science here. As I keep repeatedly saying, there are a billion ways of doing the latch and there are a billion and one ways of doing the preamp. So you connect the 2 together, there are a zillion ways of doing the preamp and latch together. So obviously it doesn't make sense for me to go on discussing everything because it's already, I think, pretty straightforward. As you can see, the basic ideas are very, very straightforward. The real, what you call, the grunge work comes during implementation, right? You got to be very careful. And as you can see here, timing is everything. If you screw up timing, things will not work at all. But what you don't want to do while debugging is to put in an input sine wave and look at the output codes. I will guarantee you that in 99% of your cases, your first design, you will see some garbage coming out. You don't expect the output codes to flip nicely like a 4-bit quantized sine wave. There will be screw up, and looking at the codes is not going to tell you anything other than the answer is not right. So what you need to do is to go, first of all, make sure that your clocks are all aligned properly, and go carefully from the input to the output in steps. You know what this should be, you know what that should be, right? You know what you're expecting at the outputs of the preamp, at the inputs of the preamp, and so on. And that's that's the only way to debug these things. And the outputs will not look nice and clean as you expect them. Due to charge injection, you should expect glitches and so on. But again, there's nothing to be alarmed about glitches. It's a way of life, right? When you have MOS switches opening and closing, you will have glitches. As long as you know what you're doing, that should be fine. This is the sequence of events that leads to one decision being made. So what do I do after LRST? What can I do now? I can go now process the next sample. So what is the maximum speed at which this particular flash can run at? This is the minimum period I need for flash operation. Alright, so let's spend a couple of minutes figuring out what this preamp dude is doing when the latch is working hard. What is he doing? The output of the preamp is only relevant when LC is high. So when LE is high, what is the preamp doing? It is still amplifying the input. One way of reducing this phi AZ time, the preamp is basically doing nothing here. Another possibility for clocking is to observe that the preamp is goofing off when the latch is making a decision, and say, I've got work for you to do. During this phase, you can actually be auto zeroing during that phase. So the preamp which was idle before is now put in auto zero mode for the whole cycle, for the entire part of the cycle where it is not required. Thereby I can speed up the flash operation, because if I know that my preamp requires so much time for auto zero, all that I need to make sure is that I can now crunch down. So the real clocking will be, so LC will begin to rise up. This is the next clock cycle. The preamp auto zero can happen. The next thing is to figure out, how can you increase the speed at which your flash can run? Reduce the time spent for each phase as much as possible. So clearly, you can crunch time by reducing LC, LE, LD, and phi AZ. LE, and if LE goes down, LD also must go down. And latch connect, of course, depends on the speed of the preamp. So the width of this guy depends on what? The regeneration time constant. Typically it will turn out that these two can be very small, because all that there is just shorting to capacitors. So LRST will be very thin sliver, so will LD. It is LE and LC which basically take up a lot of time. And the next thing I need to figure out is, what about phi AZ? Can you comment on phi AZ? Do you think the auto zero time, can you kind of estimate if it will be much smaller than LC or will it be much larger than LC or what? LC duration versus, so during LC, this is the situation, and for your reference I am just drawing the parasitic capacitances that need to be charged at the outputs of the amplifier, which include the input capacitance of what? Of the latch. Now during phi AZ what happens? So this is Vref P and these parasitic capacitors have initial conditions. What are the initial conditions? So the differential voltage across these two capacitors was A times VIP minus VIM minus A times Vref P minus Vref M, and those voltages have to come back to what value? What will be what is the steady state output voltage at the end of phi AZ? The output voltage at the preamp, okay, at the end of the auto zero phase, you are expecting it to be P offset. These voltages which were large, or could be large because it's A times something, are expected to come down to something close to 0. If you assume offset is 0, then they are supposed to come together. So what do you think the time constant of that process is going to be? Do you think it's going to be higher than before or it's going to be lower than before? I mean, in comparison to the time duration you have for LC, do you think it would take more time to do that now, or do you think it would take less time to do that now? It will take more time. Why? The input incrementally is constant. So see, I mean, the load to the amplifier in this case is simply CP. But the load in this case is now what? Okay, one thing is to notice that the load on at the output of the amplifier is now much larger during the auto zero phase than during the amplifier phase. So in principle, the poles in the circuit diagram on the right will be much smaller than the poles during the latch connect phase. So without thinking, you could say that the phase on the right, the time constants will be, it simply takes a longer time to charge up a larger capacitance, bottom line. One observation is that the big capacitors are already charged to almost what they would need to be. It's only the small capacitance that has to be discharged. To that degree, yes, you're doing definitely better than you would be doing if the big capacitors were also charged to a different voltage. But at any rate, you will find that in most practical cases, this is what will dominate, and you will find that the time constant for auto zeroing can be many times larger than the time constant during the amplifier phase. I mean, this we have not yet delved gone into the details of the amplifier. When we get into the details, I guess you'll be able to appreciate this more. So far we have assumed that the preamp is some kind of voltage controlled voltage source with some finite bandwidth. And it turns out that the easiest thing to do is make it a voltage controlled current source. But so what matters is the gain bandwidth product. So I mean, is this good news or bad news? So when do you want to use a flash? I mean, when you use a flash, it means that you want to get the job done as quickly as possible, and you're basically getting limited by this silly auto zero phase, which is required to store the offset. Okay, it's eating up a lot of your time. In fact, it is eating up, in principle, it will often require many times more time than the LC and LE and LD and all this put together. So the speed of the comparator is getting severely limited by the process of auto zero. Of course, you could definitely make things faster by making the bandwidth of the preamp higher. But still, I mean, if you're able to make a faster preamp, then even LC will come down. So that's not what you call a real solution. I mean, clearly, if you think about it, as you probably concluded, a lot of other designers also concluded that this auto zero is basically the problem. And it kind of seems silly to kind of auto zero the preamplifier every cycle. Why? If the offset is the same every cycle, what is the point going on asking the preamp every cycle, what is your offset, what is your offset, what is your offset? You might as well ask once, store it, and refresh it only the moment after some time you tend to forget things. So, if you store it on a capacitor, that charge will leak off after a long time. But until that time, you don't have to go on asking the preamp, it's the offset. In other words, this is equivalent to saying that I will share this phi auto zero across several cycles. Okay, and in practice, it turns out that if you go and do the math on the leakage across a capacitor and for typical values of capacitance that you use, you will find that you will be able to store this information on these capacitors for several milliseconds. So that basically means that you have to refresh offset in a comparator only at the rate of several kilohertz to several tens of kilohertz. This leads to a whole bunch of schemes which basically auto zero a comparator only once in several thousands of cycles. Okay, so it's not happening every cycle, but I'm not going to get into the details of the discussion. The only thing I want to motivate here is that the auto zero operation takes up a lot of time. This reduces the time available for conversion, which means that this limits the maximum speed achievable. So one idea, so you auto zero the comparator only once in a while. The reason why this can be done is because offsets do not change with time, or even if they do, they probably change when the temperature of the chip changes and all that, which is a very, very slow process compared to the rate at which you are doing the A to D conversion. There are many ways of doing this. So all these come under the so-called. So one way of doing this is to do this in the background. Okay, by background, this is what I mean. So let's say you have a 6-bit flash, you have 64 comparators, and you know that the comparator offset needs to be corrected. One way of doing this is to pull one of the comparators outside, I mean not literally, but in principle electrically remove the comparator you want to auto zero from the array, put that comparator which you want to auto zero into this auto zero mode, where you close the feedback loop around the comparator. But you removed a comparator from the array, which means what, so now the array is broken, right? So what should you do? You could have one extra comparator which has already been auto zeroed, and when this guy is undergoing repair, you use the extra guy. So that is one idea. The same idea can be implemented in many, many ways. So if you go and search for papers on flash, and do say search for background offset correction, you will come up with a whole bunch of papers where each author has basically tried his own secret sauce to make things work efficiently. But the basic idea, as you can see, is quite straightforward. You can basically put in a replacement. Once you have a replacement, you know the replacement will work, right? So you can take your own sweet time to go and auto zero the fellow that you pulled out of the array. So this is often called background offset correction. Why is it called background? Because the user doesn't know that this offset correction is happening. Alright, he doesn't know that you're pulling comparators out and all that. One by one, you keep pulling people out, fixing them, putting them back in. Now, there's another thing. In many systems, it turns out that the A to D converter itself is not being used for a long time once in a while. Okay, let's say and this happens, I can give you many examples. One example is this video thing. So how does a TV work? You scan from left to right, and then you blank, and then you go back and start scanning again. During the time that you blank, that I mean you don't need anything. So that during that time you can do housekeeping. You clean up offsets, you clean up gain error, you know whatever you want, and that's a fairly long time. These are called foreground offset correction. The ADC is unavailable for conversion every once in a while. Well, the definition of once in a while depends on, of course, the system. So this is the state in video, and not only that, once you come back, you trace the entire screen, you go back up. So that is also a long time. You have, I mean, in many systems, fundamentally there are slots available during which nothing is happening, and in such cases you can always do all your housekeeping during that time. The same thing happens in even in wireless systems. So the receiver is most of the time in sleep mode, right? There's a lot of time to basically do a lot of housekeeping, and in fact that's what is done. So a lot of calibration, all that stuff goes on during those blank intervals, and then when you wake up, you're all ready for action because all your errors have been corrected out, and so on. In fact, the same thing also happens. It turns out that in the disk drive read channel, it turns out that due to the way the system is built, there are intervals during which you don't need to read. For example, see this disk drive platter is pretty heavy magnetic material, and this magnetic read head is some light thing which is floating on an air column between the drive and the head. If the drive wasn't moving, the head would go and hit the platter. I guess whatever viscosity or friction or whatever causes from the read head to lift off from the disk when the disk is spinning. I mean the widths of these tracks are a few microns. So you need very, very precise position control of the head. Otherwise you'll be reading totally random sectors without knowing what you're doing. So there is something called a servo, which is basically a negative feedback loop, which figures out whether you're right in the middle of the track, or if you veer off to the left or the right. There's a way of figuring out whether you're veered off to the left or veered off to the right, and there's control for the head position, which goes and makes sure that you're always reading right bang on in the middle of the track and not goofing off to the left or the right. So this happens. So there are so-called servo tracks on the left and right which give you this information. When you're changing sectors, it hardly makes sense for you to read during every change, right? I mean you're reading disk, stuff at the edge of the disk, then you have to go and seek something in the center. It doesn't make sense for me to go and read everything in the middle. So these are all within quotes blanking intervals for the data converter or for the system. So any housekeeping that needs to be done, like auto zero, things like that, can all be done during that time. And historically, of course, because most of us work in vacuum, right? So we just want to make the ADC work. We don't really think about how to make. We don't really know much about the system, right? Because the system guy doesn't know anything about circuits. So that guy will say, give me an ADC, and you'll be designing the ADC, and then you find that the system guy wants some ridiculous speed, and you know that to do auto zero and all this, it takes hell of a lot of time. People were fighting this for a long time, and suddenly some smart elect figured that there are whole times in the system when you do not require the ADC at all. So it doesn't make sense to burn your fingers and burn a lot of power trying to auto zero every cycle. And then they figured out there was this interval where you could do the auto zero. Then they were able to increase speed dramatically because you've lost this. You now only need to have enough time for LC, LE, latch reset. So once, so if I assume that magically the auto zero has been done some time ago, the timing diagram. So if auto zero is done in the background, the timing diagram can be modified as follows. So this is LC, this is LE, this is LD, this is the time during which you grab the data, regenerated data on the inverters following, you hold on to that data, and this is the LRST. And you can see the minimum time required is a lot lesser now, and of course that's partly because I shrunk LC and LE from the previous diagram. So the preamp is amplifying here. Okay, the output of the preamp is relevant at all times. It is Vin minus. So this is when the output of the preamp is relevant as far as the decision is concerned. So the decision is made. Last job, which is to figure out whether the differential input is greater than 0 or less than 0, operates on the output of the preamp at the end of the falling edge of LC. So far I have assumed that the input is continuous time. So equivalently the sampling instant is what now? What is the sampling instant of the A to D converter? The fall of LC is the sampling instant of the A to D converter. I mean, if you assume that the comparators are directly connected to the continuous time input. Okay, so you can see that there is indeed the comparator, which is the combination of the preamp and the latch. Sampling is inherent in the comparator. So in principle there seems to be no need for an extra sampler node. In practice you will find that's a very terrible thing, but I mean there's nothing you can do if things go wrong here. So sampling happens at the falling edge of LC. And when is the output available? The output is available a little after LD goes up. So what is the so-called delay or latency of the flash? The delay of the flash is simply the time it takes between the sampling instant and when the decision is available. And you can see that the thing is available within less than a clock cycle away. The delay of the flash can be, in principle, it's just one regeneration time plus a couple of inverter delays, alright. But in practice you will need, after this you have a thermometer to 1 of n and 1 of n to binary and all that. So that's a couple of more layers of logic. So I mean the latency will be, you add a few more layers of combinational logic delay to this, but you can see that there is no, I mean you don't need to wait for another clock edge to get the output. Does that make sense? So this in principle should is a dot zero version of a flash converter with the entire works, right? There is a preamp, there is a latch, offset of the preamp is cancelled. Even if, I mean for a first look it seems as if, since there is sampling inherent in the preamp operation, in the preamp latch combo, there is in principle no need for a separate sampler node. The last thing we need to look at is look into some preamps. Let's do that. The simplest thing you can think of is, let me call this 0. So the input common mode, and you know that during auto 0 what happens? This is what happens during auto 0. So what is the input common mode of the input common mode is the same as the output common mode and is nothing but VDD minus, and the gain is nothing but GMR, differential input to differential output. So the only way to increase gain, if you want to keep the transistors and the tail current source fixed, the only way to increase gain is to increase R. And what is the problem with that? The output common mode will keep going down and eventually it will crush the current source. So that's no good. An improved version is to, so large gain is problematic because the common mode will go too low. So what do we do? You can use a current source, use an active load. Alright. So what should this behave like? This transistor should behave like a current source of value I, and so should this transistor. Okay, but in our whole discussion on fully differential amplifiers, we have said that it is not possible for this tail current 2I to be exactly balanced by two independent current sources of value I pushing in from the top, because the moment one is smaller than the other or one is larger than the other, they will cause the output common mode voltage to either go float up to VDD or get pulled down to ground. So you need to make one set of current sources dependent on the other. You got to make, measure one current source and make sure that it's exactly equal to the other, and this is nothing but some kind of feedback loop, and since this is applied to common mode signals, this is called the common mode feedback loop. Simple way of doing it without having, you could put an op amp and all, you put an error amplifier and the usual negative feedback loop stuff, but there are many ways in which you can get the feedback loop is not drawn as a block diagram, but it is inherent in the circuit itself. One example is this guy here. If I want to find the common mode equivalent, what would I want to do? So the common mode equivalent circuit is to draw only one half. The resistors, the two resistors don't appear in the diagram simply because no current flows if I yank both the input nodes up or down because of mirror symmetry. The output nodes will also go up by the same amount, which means that there is no current flowing through the resistors, correct? So the common mode equivalent circuit is there as shown on the right. And so what is the common mode output voltage? It is VDD minus VSG of the transistor. Before I get to the differential part, what is this? It's VDD minus VTP plus the overdrive, okay, which I call delta V. Now, what happens in the differential mode equivalent? What is the differential mode equivalent circuit? Incrementally equivalent circuit. I want to find the differential incremental gain. You connect the gate voltage of PMOS to ground. So if I assume that the output impedance of the PMOS transistors is infinity, then equivalently I have. So this is the differential mode equivalent. So the gain, differential mode, the gain is still GMR. However, what is the difference between this and the earlier case? Now in principle you can increase R limit without a limit, okay. The common mode doesn't change. The common mode output is independent, as you can see, of R, because R doesn't appear in the common mode equivalent circuit at all. Alright. So this breaks the dependence of the output common mode on the load resistance, thereby giving you an opportunity to increase the differential mode gain without any consequences on the output common mode level at all. Okay, so now I get greedy. I want even more differential gain. Right? I know how to. Now I know that with a common mode feedback loop, I can make the output common mode level independent in principle of the differential load, right? So the next thing is to say, hey, what can I do to make the gain? I know that I want a large gain, right? So what can I do to make the gain even larger? I go on making R larger and larger and larger, but unfortunately you know that R is nothing but some rho L by A, right? On an IC it turns out that you can't do anything about the area of cross section. A resistor is nothing but some kind of wire, right? You can't do anything about the cross section of the wire. Only thing you can do is make the wire longer and longer and long, correct? So a large resistor basically means a large area, okay, and a long wire, also has a lot of parasitic capacitance, as you can all, at least even if you don't know, you can agree, right? The moment you start making R larger and larger and larger, you end up with this dual problem of both increased capacitance at the output and also the area of, each of these preamps becomes a big affair because of the resistors. So the question is there something we can do to fix the problem? That is, you want a large resistance, without using a large resistor. One way is to say, okay, is to go back to our original common mode feedback loop and say, I'm going to somehow measure common mode voltage, average it, and do this, right? Compare it with VCM ref, okay? This is the classical thing, right? There's a straightforward implementation of the block diagram itself. The problem with this is its complexity, right? Because for every please note that you have 63 preamps and a 6-bit flash, right? What do you think the signs on this for the umpteenth time? What are the signs on this guy? The left is what? Plus. What is the differential gain? If the transistors have infinite output impedance, the gain is infinity. In practice, it is GM by, it is ROP of the PMOS parallel the RON of the NMOS. Correct? So this is the best you can do. You can't expect to get, for the cheap transistors that you have, you can't expect to do any better than GM times ROP parallel RON. Okay. So the question is, can you get GM times ROP parallel RON without having all this extra paraphernalia around the does this make sense? Okay. So what do you think is a reasonable direction to start? By looking at these two diagrams, if I use resistors to sense the common mode, I get screwed up because the resistors also load the differential output. Okay. So how did I avoid that here? By conveniently putting a VCVS. Okay. So the bottom line is, in order not to affect the differential gain, I shouldn't be sensing the common mode using a resistive divider. Okay. I should try and figure out some other smart way of doing it where a resistor doesn't touch the drains of the transistor. Again, as I keep saying, there are any number of ways of doing this. Let me just put down a couple of them. So one way of controlling the current, in this case we saw that we want to make the push in current equal to the pull down current. Therefore, we needed a variable current source, and the way of making the variable current source was to go and vary you pull the gate up and down. So there is no earthly, so you know that the current in the drain current of the PMOS transistor depends on what all? It depends on the source gate voltage. So there is no particular, nothing holy about the gate. I could have as well kept the gate fixed and wiggle the source. So that's what this is up to. So for example, let me take a let me call this some fixed voltage V bias. To change the current, if I keep the gate fixed, right? One way of changing the current is to add a variable resistor there. Okay, if I increase the resistance, what happens to the current? If I increase this variable resistance R, if I increase R, the current will reduce. If I reduce R, the current will increase. Okay, fine. Now, how should the R be varied? So that's my knob to which to turn. It should be turned depending on the common mode voltage. So if the common mode voltage goes too high, VCM is too high, what should I do? it basically means that the current being pushed down is too much, so I must increase R. If VCM is too low, one must decrease R. Alright. So this R must be somehow related to the output common mode voltage. Correct? So any ideas? Okay. One idea is you put a PMOS and connect what to the gate? Or a PMOS. So what will you choose? Why PMOS? Please note that if this common mode voltage goes up, you want the resistance to increase. So will that happen with a NMOS transistor or a PMOS transistor? Okay, so it got to be a PMOS. Great. Okay, so if I somehow knew the common mode voltage, if the common mode voltage goes up, then the resistance will go up, thereby current will reduce, causing the common mode voltage to go down. So the problem is to get the common mode voltage here. Alright. So one suggestion was to tie this to the output, but clearly there are two outputs. And please note that while the common mode is not just any one terminal, but the average of two terminal voltages. Okay, so put one more PMOS. Does it make sense? Alright, so neither resistance, so this is the common mode feedback loop is the transistors drawn in red. Alright, the conductance, assuming the transistors are in triode, the conductance of this chap is mu p C ox W by L times E, let me call this VOP, this is VOM, minus VOP minus S minus ETP. And the conductance of this character here is mu p C ox W by L times VDD minus VOM minus VTP. Okay, and therefore the total resistance here is the two conductances in parallel, right? So it is simply adding up the two. So the conductance of the combined branch is mu p C ox W by L times VDD minus VCM at the output minus VT. So in other words, you are implicitly converting from, you're only tapping off both VOP and VOM, alright, but when VOP goes up, VOM goes down, alright. So if the common mode voltage at the output is what you want it to be, then, or it's around the equilibrium point, an equal and opposite change in the output, in other words a purely differential output, as you can see from the simple formula, will cause the conductance of this resistor to remain unchanged, right. So this common mode feedback loop becomes active only when there is a common mode change at the output. You want the common mode feedback loop to just shut up and keep quiet when there is purely differential operation at the output. You want it to get into action only when there is a common mode change, and you can see that happens here. Differentially, what is the peak to peak swing possible? This node can go up by to a maximum of V bias plus VTP and go as low as Vin minus Vtn. But the crucial question is, what is the value of common mode? I mean, it's clear that there is negative feedback, correct? But what is the value of the common mode voltage at the output, or is there a clean way of setting the output common mode to some voltage you want? So what do you think is what is the only if I fix all these sizes, what do you think is the only knob you have to change the common mode voltage? V bias. Okay. So the name of the game now is to figure out, the next job is to figure out how I should generate V bias such that this output common mode will remain what you want. Okay, so this is V bias. Alright, so what is VCMO? So if I gave you V bias and let's say the W by L M1 A and M1 B, this is 2I, M2 A and M2 B, and the gate voltage of the PMOS transistors is V bias. So what do you think, so from this can I figure out what VCM out will be? Yes, it is certainly VCM out. The observation to make is VCM out is equal to VDD minus VSG of M1. I mean A or B doesn't matter because it's the same thing. Yes, what next? Okay, so let me call the W by L of this transistor equal to 1, and similarly that of M2 to be W by L of 2. Okay, so what else? How do I find? So how will I find VSG of M1? We know, let me call this voltage Vx. Okay, Vx is known. Why? Is V bias is known, plus, and we know that M2 operates in saturation. So Vx is nothing but V bias plus let me see, plus VTP plus, let me call this the overdrive of transistor 2. Okay, this is nothing but VSG of M2. You know the current, you know Vx, okay, so what? You know that the transistor M1 is in the triode region, so what do you do? So M1 is in triode, okay, so what? So you know that its resistance is 1 over mu p C ox W by L times VDD minus VCM out minus VTP. The denominator is the conductance of the transistor. So 1 over that, the conductance is the resistance of the transistor. Okay, that times I must be equal to this times this is nothing but VDD minus. Alright, so as we agreed, this is known, this is known, all these are known, so you can go and find, and this is known, so the only thing to find is VCM out. So the question is, in practice you want to set the output common mode to some desired value VCM ref, alright. you don't want to go on calculating, doing this math, alright. So the clean thing is to ask the question, what should V bias be so that the output common mode will be some VCM ref that I want. You understand? I mean, given that if I want VCM out to be some desired quantity, how will I go and find VCM ref? How will I go and find V bias? So in this equation I will plug in VCM out equal to the voltage I want, which happens to be 0.9 volts. From this I will get Vx, okay. I plop in Vx into the top formula, right, and then get, I know delta V2 because then I will be able to get V bias, alright. So one observation is to say, if this was VCM desired, a VCM ref, okay, alright. So this, as I said, this size was W by L1, each of these transistors. So if I put a transistor of size W by L1, another transistor of size W by L2, okay, and then I pulled out a current of I, alright, this voltage will remain exactly equal to this voltage will remain fixed only when the current being pushed in is, this voltage will stay put at a constant value only when this current is exactly equal to I, okay. Alright. So if the V bias is too low, what do you think will happen? This node voltage will go up. If the V bias I have applied is too high, node voltage will go down. So if this remains at a constant potential, V bias will be the correct voltage, okay. So which means, what should I mean? So if this node voltage, in other words, if this node voltage is going down, what should I do to V bias to hold that, to prevent it from going down? I should pull V bias down. On the other hand, if this node voltage is going up, I should increase it, right? So what is the straightforward thing to do? So to derive V bias, all I need to do is to connect the two this way. Alright. So this is the V bias and I just simply connect it this way. This is called replica bias. Okay, so this branch on the side is nothing but a scaled version of this character here. Okay. The current densities in all those transistors is identical to the densities of the current in the main branch. Okay. In principle, I could have made this 2I and 2W by L1 and 2W by L2, or I by 2 and 1/2 W by L1 and 1/2 W by L2. Nothing will change. Okay. So this is the so-called replica bias. Okay. And the advantage of this is, of course, that you are able to set the output common mode voltage to something desired, to a known value, to a known reference, without having the complete extra baggage that comes with explicitly sensing the common mode using, some kind of resistive averaging, using an error amplifier and all this other stuff. Okay. All right. The disadvantage is, it turns out that if you go and do the loop gain for the common mode feedback loop, it turns out that it is not as large as what you would get with an explicit amplifier. Okay. And you just need to generate one V bias and circulate it to all the preamplifiers. That's quite straightforward, because this branch, the replica bias branch on the right, can be common for the entire array of preamps. Okay, so it's not really, you're not replicating one guy for every preamp. And this is actually a quite a popular technique, not only just in preamps but in circuit design. A lot of times where you want some simple cheap common mode feedback, this is not a bad thing at all to do. Okay, you have to choose sizes W by L1 and W by L2 appropriately, so that the transistors on top are in triode. Okay. So what do you think if there will happen if the transistors are not in triode? If they
averaging is not true.
If they were in saturation, I mean, if they're not in triode, they must be in saturation, correct? So what do you think will happen if
in differential mode the current is
correct? So ideally you want the common mode feedback loop to be active only when the output common mode moves. For differential mode signals, for balanced signals in other words, okay, the common mode feedback loop must not be active at all. In this case we saw clearly that that indeed happens, right? Because when there's purely differential operation, when one voltage goes up and the other voltage comes down, the conductance of one of the transistors increases, the other one decreases, the total conductance remains the same, which means that the common mode component of the current being pushed remains the same. Is that clear? So this is one, again, this is a fairly popular candidate for using as a preamp, all right, and and one thing that you must bear in mind is that, see, the difficulty with the flash occurs only when, with the comparator occurs only when the input is, when the input is lying very close to a reference level. All the other comparators, it's an open and shut case. Okay, all right. It's only that one comparator which is sitting closest to whose reference is closest to the input, which is the crucial one. All right. So in other words, if this particular comparator was crucial, then what can you say about the differential input between these two nodes? These are the inputs to the preamp, correct? So the comparator which is crucial in which helps you make the correct decision, will always have small inputs. Okay, so it is so all this we have talked about only are small signal gain and all this other stuff. GMR is a small signal gain, right? So the comparator which makes the correct decision, okay, which is crucial in you getting the right code, always will see a small input, which is why it makes sense to talk about small signal quantities. Okay, the comparators which are far away from the reference, okay, they have a large signal at the input, but the signal is so large that there is hardly any difference in making the right decision. Okay, so this covers preamps, latches, and again, as I said, the latch is is vast, and you can but at this point you should be comfortable reading a flash paper.